Okay, let's continue with the second section on mean value properties and maximum principles. So, firstly, we have the definition of means. Mean is just an old word for the average, and in this course, when we say mean, we sometimes mean weighted average of this special form. Generically, it has this particular thing. So we're just going to use M for some sort of a general mean. What it is an integral over some function u, of some function u, over some particular set with some particular weight. So to name some particular examples, if we have the Laplace equation or the wave equation, we consider spherical means, so that the set we're integrating over here is a sphere. This weight function is just always 1. And what we have in front is called a normalization constant, and the normalization constant is set to be n times the volume of the unit n ball times the radius to the power of n minus 1. So the mean is a function of three things. It's a function of a particular function u, so it takes a particular function u. It's a function of what's called the center point, or the middle point, in this case x, and of a radius. Right, so we actually think of a family of means for different radiuses. So the center point, or the set that we're integrating over, it depends both on the center point and on the radius. And what it should look like is it should look like some set which depends on the radius, and it should just be translated to the center point. Okay, so that's what we see here for balls. We have a generic ball of radius r, and then when we put the x here, we mean that it's centered at x, or the standard ball centered at the origin is translated to be centered at x. And that's what we see for the heat ball as well. We define some particular heat ball, and then we translate it to x and t. Right. So sometimes the center point, we separate the space and time variables, as is common in problems to consider space and time variables separately. So in this case, it's translated to be centered at xt, and we know that centered actually means the heat ball looks like kind of like this, right? It's kind of a wonky shape. The center is actually at the top on the boundary. Okay. So for the spherical means, we have weight 1. For the heat ball, we have this other weight function, which is determined by some sort of intrinsic scaling property of the heat equation. In the spherical case, here the space and time sort of have a scaling of 1, but we saw that there was this other scaling property for the heat equation, and so this is somewhat motivating why we need a different weight function. We can actually see that here with the definition of the mean value property. We have our normalization in front. We have the integrating over the heat ball, the function u, and we have the weight function x squared on t squared translated so that it's centered at the translation point as well. Okay, then. So let's then talk about the normalization constant. The normalization constant is just set to be the value of this integral when you take the function 1. Right? So you can imagine a function 1 here. And why we have this normalization property is so that we have this property of means always that the average of a constant is just the same constant. So if we put in the definition a constant function c at some point centered at some point x with some radius r, what we see is we have cr inverse integral over x plus ar 1 weight of y minus x, and then dy, integrating over the y coordinate. But then you can make a change of coordinates here. Let's say z. Then this will be CR inverse, just integration over this base set now of the weight function, like so. And that is by definition what this normalization constant is. So you just get CR over CR, which is 1. Oh, I'll do it. Maybe I'll do it with 1 here. Yeah, and then if you had any other constant, you can see that because the integral is linear, you just get that same constant at the end. So this normalization is so that we have this property that the average of a constant is the same constant. Okay. So that's something that's nice, and that's something that we use a little bit. We also have this very important property that for continuous functions u, if we take the limit as the radius goes to 0, what we get is just u at that center point. Okay, and so there are a few assumptions that go into proving this. Obviously, continuity. But you'll notice that the sets AR, they kind of go to 0, right? They contract to the point 0, and so their translations contract to the point x. And this is important. So we can sort of write a general proof here of this property. So by continuity, for all epsilon greater than 0, there is some delta greater than 0, so that for all y in a ball centered at x of radius delta, f of y minus f of x is less than epsilon. Or to write this a different way, without the absolute value, we could write that f of x minus epsilon is less than f of y is less than f of x plus epsilon. So in other words, the value of the function at any point y in a neighborhood of x is the value of the function at x plus minus epsilon, or lies within epsilon of the value at the center. So if we assume, which is always the case, that the weight function is positive, or non-negative is enough, then because this is an integral, we have inequality of integrals. And so when we can integrate this, and we can have m of f of x minus epsilon. So this is just a constant centered at x of radius r is less than m of, I changed from f to u, but you'll follow me, is less than m of f of x plus epsilon radius r. So here we've integrated over y. We've multiplied everything by the weight function. We've now integrated over y over this set, and then divided by the normalization constant. By this property of constants, what we have on the left-hand side is f of x minus epsilon. We have in the middle the mean of f at x of radius over the radius r. And then on this side we have f of x plus epsilon, because again, I'll use a different color here, and here we have constants in y, all right, which is what we integrated over. So when we do that, what we see is that for all epsilon greater than 0, the mean value lies close to f of x, and that in particular means we have this limiting behavior, like so. And so this assumption that the set we integrate over goes to 0, this is necessary because this holds for all r, this inequality holds for all r, such that AR is a subset of B is a subset of this neighborhood, right? So for sufficiently small R, these sets have to lie in a neighborhood of the point, and then this inequality holds for all such points, and so then we can integrate over all such points. But what we see is for the heat ball and for the normal ball, these do in fact contract to a point uniformly, so this assumption is valid there as well. So we see this proof several times throughout the script, and it's really the same proof every time, using this more general notation and assumptions here. Okay, so we have this mean. What should we do with it? So one question we can have for the mean is, how does the mean change as we change the function r? Okay, so how it changes is different for different means and different assumptions on u. So whether u satisfies a Laplace equation or a heat equation or the wave equation or so on. But let's look at the proof for the mean value property 3.3, which applies to harmonic functions. So the assumptions that we're making in mean value property 3.3 is that u is twice continuously differentiable and u solves the Laplace equation. The Laplacian is equal to 0. So what we have inside is we've just taken the definition of mean and we've applied a slight coordinate transformation to put it into this form. The advantage of this form is that the domain of integration now no longer depends on r. So we've sort of rescaled so the domain doesn't depend on r. And this means that we can easily bring the partial differentiation with respect to r inside the integral. So that gives us 1 on an r integral over a sphere of radius 1 centered at the origin of the r derivative of x plus rz d sigma z. Now, if you recall from the previous section, we spent quite a bit of time looking at how to calculate derivatives of this form using the chain rule. And what we saw there was that we should write this as the gradient of u dot product with the coordinate change derived with respect to r. Okay, now this is relatively easy because this is just x plus rz derived with respect to r just gives us z. So we have this. And now what we have to recognize is, because this is the unit ball centered at the origin, z, if we just think about the unit ball and we think of this vector, say z, pointing from the origin to a point on the ball, if we translate this vector, which we can always do for vectors, we have, it's a bit large, we have an outward pointing, it's perpendicular to the circle and it's length 1, so z is in fact the outward pointing unit normal of the of S1. So having made this recognition, we see now that this is actually in the form that we can apply the divergence theorem to. So this is the integral over the boundary. This should be equal to this integral over the interior space of the divergence, nabla dot, of the gradient of u. Like this, and I'll leave off the dx or the integration tag. Now we know from vector calculus, we did some vector calculus exercises as well, that the divergence of the gradient is the Laplacian. And what is one of our assumptions? One of our assumptions is that the Laplacian is 0, so this is equal to 0. So what have we calculated here? We've calculated that the spherical mean of a harmonic function, something that satisfies the Laplace equation, is 0 with respect to the radius. So as you change the radius, the spherical mean does not change. This is really surprising, I think, but very useful. So we can answer this question: what is drm in this case? Drm is equal to 0 for a harmonic function. We see the same thing with the heat equation. All right, so this is now the second point here. Harmonic functions are their spherical means don't change. The spherical means of heat functions don't change as well. The spherical means of wave equations do change as you change the radius, but how they change is governed by this so-called Euler-Poisson-Darboux equation, which we'll discuss later. And the proof that they obey such equation is lemma 5.2. So we take this fact that the spherical, that the derivative of the spherical mean is 0. This means it's a constant. If we put this together with this property that we proved up here, that the limit as r goes to 0 is just the value at the center. If this is constant on the left-hand side, what we end up with is that this constant here is equal to the value at the center. So we get u of x is equal to the mean of u with radius r for all r, I guess on the assumption that the ball of radius r is a subset of the domain where it's defined. Or I should say the sphere of radius r is a subset here. Yeah, so this is some very nice property. This is called the mean value property. Okay. Why is this a very nice property? Because it allows us to prove the maximum principle very easily. It also gives us Liouville's theorem, which we will talk about later as well. So what is the maximum principle? The maximum principle is that harmonic functions are not allowed to have maximums, or not allowed to have maximum points, except maybe at the boundary. And maximum principles hold for elliptic and parabolic equations. We saw in exercise 24, this back in the saddle question, just from calculating directly at a single point, knowing that the Laplace equation holds at a single point, that under the assumption that the critical point or the turning point of the function was non-degenerate, so some additional assumption, that it had to be at a saddle point. Okay, we know that functions critical points can be either local minima, local maxima, or saddle points. So the fact that it has to be a saddle point means it's not a local minima or a local maxima. So that's sort of explaining the connection to the maximum principle part of this question 24. And you can read through the solution to that question if you like. So we can prove, though, with the mean value property, without that additional assumption, that there are no local maximas and minimas. Okay. So I've broken this up a little bit differently to the script. I've put in an extra point. I've put in something called the local maximum principle that's not in the script. And then as in the script, we have the strong maximum principle and the weak maximum principle. Okay, so what I want to do is I want to explain what this local maximum principle is. It's that if you have a point u that has a maximum at x, then in the case of harmonic functions or the Laplace equation in blue, then it has to be constant on a ball surrounding that point. Or for the heat equation in red, get it red, heat, then it has to be constant on a heat ball centered at x that lies in the parabolic domain. Okay, and you can understand why I want to call these local principles, because if you have it at some point, then you know it on either some ball centered at that point or some heat ball centered at that point. So it's sort of just a local statement. And this is let's recall now how the proof of this goes. So what you should do is you should suppose that U has a maximum at X. And what does that mean? That means that near X, let's define a function v of y to be u of x minus u of y. So you take the maximum value away from the value at the point you want to consider. And by assumption that u of x is always bigger than u of y near x, this is greater than or equal to 0. Okay, so what we should do now, though, is because this is a constant and, let's say, a harmonic function in the case of the blue condition, or a constant and a solution to the heat equation in the case of red, we know that the mean value property holds. So what we can say is we can say that v at x, which is 0, right? It'll be u of x minus u of x, is equal to the mean value of v on some radius r. Okay? And if we write out what this means, it means that, okay, so there's some normalization constant. Let's do this for the blue case, r to the n minus 1. Actually, you should do it for the ball mean in the case of the Laplace equation, not the spherical mean. V of y dy. And so what we have now is we have an integral of a non-negative function that always gives 0. And then you need to make an argument either similar to lemma 2.9, the fundamental theorem of the calculus of variations, or by some local continuity argument that this implies that v of y has to be equal to 0. I'm pretty sure the continuity argument is written in the solution to exercise 25a. All right, prove that every subharmonic function obeys the maximum principle. I think this argument is in the solution to that part of the question, if you want to recall why that argument holds. And of course, the fact that v is equal to 0 is equivalent to the fact that u of x is equal to u of y for all points in the ball. Okay, so we get this. And for the heat equation, the proof is entirely similar. All right, except it'll be the heat ball here instead of a normal ball. But this step of going from the fact that 0 is equal to some integral of a non-zero function implies that that non-zero function is in fact 0 almost everywhere. That is the same whether you want to use it for the Laplace equation or for the heat equation. So this is how you can go from the mean value principle to the local maximum principle. Now to go from the fact that if you have a maximum at one point to you have a maximum on a path-connected set, then that's when you need to apply this argument of choose a path that connects this point where you have the maximum to any other point, cover that path by balls, and on each ball apply the local maximum principle in turn. And this then spreads it from not just a ball or a neighborhood of the point to every point along this curve, and therefore every point in the domain. So if you like, in the script, this argument is part of the proof of the strong maximum principle, and I've just given this part of the argument a different name. And then to go from the local maximum to the strong maximum, you apply the second part of that argument with the covering of the path by balls. Okay. The point that we've noted before as well is because the so-called center of the heat ball, x, or I should say xt, lies on the top edge of the heat ball, then if you have a parabolic cylinder, omega t, and a point on the top edge of the parabolic cylinder, the heat ball lies inside the parabolic cylinder. Okay? So this also applies, this maximum principle also applies to points that lie on the top edge of the parabolic cylinder, and that's the reason that we include the top edge in the parabolic cylinder in that definition. So that's sort of providing motivation of why we defined it this way at the start. So that all points on the parabolic cylinder, including these points at the top edge, have the strong maximum principle. Okay, so one way to think of the strong maximum principle is it's not telling you something about a function, or so to speak, right? Okay, it is if the function has a maximum in the interior, then it's constant. What you should do, though, is you should think of this as telling you what functions don't exist. Right? The strong maximum principle tells you that there are not functions with a maximum, that there are not interesting functions with a maximum on the interior of the domain. Right? It eliminates the possibility of those functions. So what you have left is either you have the constant functions, or you have functions whose maximum occurs on the boundary of the domain. Right? So you should understand the strong maximum principle as eliminating one type of function, right? Functions with maximum on the interior that are non-constant. So for that reason, we usually use it in the form of the weak maximum principle, right? Which tells us something about functions. Like if you have a particular solution, it tells you something about that solution. It tells you either the solution is constant or the solution has a maximum on the boundary of its domain, in the case that the domain is bounded. Okay, because if the domain is bounded and your solution is continuous, you know that it has to have a maximum somewhere, right? Continuous functions on closed and bounded sets have to have a maximum. And if it cannot be on the interior, then it has to be on the boundary. So this is how you take the strong maximum principle and use it to tell you something about the function that's actually your solution you have. Why the weak maximum principle is so useful is it sort of it very quickly gives us uniqueness for the Dirichlet problem. So let's consider the Dirichlet problem for Laplace's equation, and we have that. Let's say u is equal to g on the boundary of the domain omega. Here we have omega. And this is a bounded, omega is in a bounded open domain. So if we have two different solutions, what we should do is we should look at V, which is U1 minus U2, where U1 and U2 are the different solutions. And we can ask what partial differential equation and what boundary value problem does V solve? Okay, well, V still solves Laplace's equation because Laplace's equation is linear and V is the difference of two solutions. Except now on the boundary, it's equal to G minus G, which is 0. For the boundary. So what we should do is we should consider this function V, which is a harmonic function that is 0 on the boundary of this region. Now, we know by the maximum principle, or the weak maximum principle, I should say, that therefore the maximum of V is 0. Okay, so that's very nice. But what we should recognize as well is that negative V also solves this. So the Laplacian of negative V is 0, and negative V is equal to 0 on the boundary as well. So the maximum of negative V is also 0, or in other words, negative the minimum of V is equal to 0. All right, because the maximum of a negative function is the negative of the minimum of the function. So you can clearly see from these two statements coming from the weak maximum principle that v has to be 0 everywhere because its maximum and its minimum is 0, so therefore it's identically 0, and therefore u1 is equal to u2. Okay. In other words, there is a unique solution to the Dirichlet problem. Okay, but that sort of tells you why we only focus on the so-called maximum principle, is because if you apply the maximum principle to the negative of a function, then you get the minimum principle, if you like. And so it's enough just to talk about one of them and then remember this trick with the negatives to get to the other one. And so then sometimes people also call this the extremer principle, right? So you can say the weak extremer principle is that on a bounded domain, any extrema are taken on the boundary. So extrema is a word for maximum or minimum. So that's very good. This gives us the uniqueness for the Dirichlet problem. And remember, regularity, uniqueness, and existence are the sort of the three questions we always ask. And it gives us the Dirichlet problem for the Laplace equation on a bounded domain, and also for the heat equation on a bounded domain, which is really nice. We can actually generalize the maximum principle to what's called subsolutions. So a subsolution, instead of looking at L of u equals 0, where L is the Laplace operator, the Laplacian, or the heat operator, we instead look for solutions which are less than or equal to 0. So let's say the sum of its second derivatives is always adds up to, at every point, is less than or equal to 0. Right? Because remember, the operator applied to u gives us another function. And often we require that to be 0. We require that to be equal to the inhomogeneous term. We can also require inequalities amongst functions. So in the last line, in the last step of the proof of the mean value property, if you look here, we use that u is equal to 0. If instead for a subharmonic function, we have the negative of u is less than or equal to 0. So what we have then from that proof is then that the derivative of the spherical mean with respect to the radius is always then greater or equal to 0. It's sort of a convention to have a minus sign here and say less than or equal to, but it's the convention that makes it fit with the heat equation as well. So we have, instead of the spherical mean being constant in the radius, we have that it's an increasing function in the radius. And so in particular, then we have the mean value property for subharmonic functions is that u of x is less than or equal to its spherical mean. All right, instead of equality, we have inequality. But this is still very useful, okay? Because this still gives us the maximum principle. So if we look up here of this local maximum principle, what we would see is we would take the same function v here, and how the inequalities work, you would still end up with the fact that this integral has to be equal to 0 when you play around with the inequalities. With this inequality and this inequality together will give you that this integral is equal to 0 still, and so you still get the local maximum principle for subharmonic functions, and the maximum principle and the weak maximum principle. What you don't get is you don't have this ability then to apply the maximum principle also to the negative of a subsolution, because the negative of a subsolution is not a subsolution anymore. It's a super solution. It has the inequality going the wrong way. So you only have the maximum principal. You don't have the minimum principal for subharmonic functions. But let's see if we try to then apply the same proof. And instead of uniqueness, what we will get is we will see that it gives us inequality of solutions. So let's do this for the heat equation, and I'll swap to red. So consider two solutions to the heat equation. And we can even make this the inhomogeneous heat equation. So the first solution satisfies the inhomogeneous heat equation with F1 or F2. For points on the boundary, it should have that ui is equal to gi, and for time equals 0, we should have ui equal hi. Okay, so this is a Dirichlet problem. We have specified the initial conditions on boundary, and we know because of how the maximum principal works for the heat equation that this is sufficient material to uniquely determine a solution to such an equation. So what we do is we take the same idea. We look at V is equal to U1 minus U2. And we ask ourselves, what partial differential equation and what boundary conditions does V obey? So we get that the heat equation, because it's linear, we get F1 minus F2. Oh, and sorry, we should make the assumption that F1 is less than F2, G1 is less than or equal to G2, H1 is less than or equal to H2. So F1 minus F2 is less than or equal to 0. This tells us that V is a subsolution to the heat equation. And then on the boundary, on the space boundary, we get that V is equal to G1 minus G2. So again, it's non-positive. And then on the initial boundary, time is equal to 0, V is equal to H1 minus H2 is less than or equal to 0. So because then we should come down here. Because V is a subsolution to the heat equation, we know that the maximum of V is on the parabolic boundary of the parabolic cylinder. All right, so here, this is what tells us that it's a subsolution, and here we have some boundary value conditions, and so that tells us then that the maximum of V is less than or equal to 0. All right, because the values on the spatial boundary and on the time boundary are less than or equal to 0, so the maximum of V, which has to be less than or equal to those, also has to be less than or equal to 0. And so that tells us then that the maximum of V is less than or equal to 0 tells us that V is less than or equal to 0, or bringing that back, U1 is less than or equal to U2 on all on the whole domain. All right, so that's what the maximum principal does. It allows us to take information on the boundary and get some information about the function on the whole domain. In this case, that there is an inequality between U1 and U2 on the whole domain. So this is how this generalization of the mean value property to subsolutions is very useful because it allows us to get inequality between solutions whose boundary value problems satisfy some inequality amongst themselves. So here we just have inequality amongst G and H and the inhomogeneous terms. Okay, there's one more thing that was covered in the course. The strong maximum principle wasn't just proved for the Laplace equation. It was actually proved for all elliptic problems, but I will leave you to read through that in the script yourself. And so then that concludes the section on the mean value properties and maximum principles.